In this video, we're going to discuss numerical differentiation. And in particular, we're going to focus on a general technique for construction of finite difference schemes. So a finite difference formula is characterized by two main things. First is the points where the functional values are used, and second is the order of accuracy. So for example, we have a finite difference scheme defined here. It uses the functional values at the points j minus 1, j, and j plus 1, and it is second order accurate. So the points where we evaluate the function can be called a stencil. So the goal for a given stencil is to construct the formula with the highest order of accuracy that involves those points. And there is a general procedure to accomplish this, which we will illustrate with an example. So for example, suppose we want to use the value of the function at the points j, j plus 1, and j plus 2 to estimate the derivative at the point j. So given the restriction of these particular points, we want to find the highest accuracy that can be achieved. So the finite difference scheme can be written in the form shown here. So the derivative of fj plus the sum of ak fj plus k from k going from 0 to 2 gives us some order of accuracy. And we've left this as a question mark for now because we want to find the highest order that is possible. And here these ak are the coefficients from linear combinations of the Taylor series. And you can see if we evaluate this k going from 0 to 2, then we get our points fj, fj plus 1, and fj plus 2, which are is the stencil that we're interested in. And we want to determine these coefficients, ak, that maximize the order of accuracy or minimize the error. So we can write these coefficients in something that is called a Taylor table, which is shown here. So how this works is the first column, if we add up all the values in the first column, we get this expression here. So fj prime plus this sum, ak fj plus k, k goes from 0 to 2. So a naught fj plus a1 fj plus 1 plus a2 fj plus 2. And then each of the rows is constructed as follows. So this fj prime is just fj prime, so we just put a 1 here. And these other rows are constructed by the Taylor series expansions about the point fj. So this, again, we said the first row is fj prime. The second row is a naught fj is just going to be a naught times fj. And then a1 fj plus 1 is we write this as the Taylor series expansion about the point fj. So it's a1 fj plus a1 h fj prime plus a1 h squared over 2 times fj double prime plus a1 h cubed over 6 times the third derivative at fj. And same for the last row here. So the Taylor series expansion of a2 times fj plus 2 is going to be a2 times fj plus 2h a2 times fj prime plus a2 times 2h over 2 fj double prime plus a2 times 2h cubed over 6 times fj triple prime. So now we can write this as the sum of the other columns. So again, we said this sum here, or if we sum up this column here, we get this expression. So this is equal to the sum of all of these times fj plus the sum of the next column times fj prime plus the sum of the next column times fj double prime plus the sum of the last column times fj triple prime. And we could do more terms if we wanted, so really we can say plus dot dot dot. So now, to get the highest accuracy, we want to set as many of these terms to 0 as we possibly can. So we want to make this right-hand side as close to 0 as we can. So we can set, we have 3 unknowns, so we can set 3 equations to 0. So we set the lower order terms to 0. So this one goes to 0, this one goes to 0, and this one goes to 0. So this gives us 3 equations with 3 unknown coefficients, which is our a0, a1, and a2. And then solving this system, we get that a1 is equal to minus 2 over h, a2 is 1 over 2h, and a0 is 3 over 2h. So now we can plug these into our expressions from the previous slides. So this here comes from expanding the sum and plugging in a0, a1, and a2. And then this comes from our right-hand side, where this is the first term that we could not set to 0. So, and you can see here that if we cancel out these, that it's second order, it's order h squared. So the resulting second order finite difference formula is given as shown here. So the first derivative at point J can be approximated with second order accuracy by evaluating minus 3fj plus 4fj plus 1 minus fj plus 2 all over 2h. So this is with the restriction of these particular points that we wanted. This was our stencil, remember, fj plus 1, and fj plus 2. With those particular points, this is the highest accuracy formula that we can get.